CS407 Numerical Analysis, Section 7.1, Ordinary Differential Equations. So, begin with the motivational example. In a simple electrical circuit, the current I in amperes is a function of time I of t. The function I of t satisfies an ordinary differential equation of the form di dt is equal to function t f of t and I. It's probably the only slide where I'll ever get to use the Euler font. I find electrical circuits to be a little bit spooky, and the I sort of looks like the cursive I that's in the book. So that's as close as we're going to get. Anyway, in this differential equation, the right-hand side is a function of t and I that depends on the circuit and the nature of the electromotive force supplied to the circuit. Let's take a look at a second motivational example where we can actually use this. And these are one of my favorites. These are predator-prey models, and they help to account for the way in which two different animal species can sometimes interact. U of t is the number of individuals in the predator species, and V of t is the number of individuals in the prey species. And if we have A, B, C, D and constants as constants, then we can have du dt is equal to A times V plus B times U, and dv dt is C times U plus D times V. So this is a pair of nonlinear ordinary differential equations that govern the populations of two species as a function of time t. In this section, we're going to develop numerical procedures for solving this type of problem and the electrical circuit problem. Of course, we'll begin with a general discussion of ordinary differential equations and their solutions, and as you may have guessed, since it is numerical analysis, we'll also take a look at some uses of Taylor series in this regard. Let's begin with ordinary differential equations. An ordinary differential equation is an equation that involves one or more derivatives of an unknown function. The solution of a differential equation is a specific function that satisfies the equation. Now, in the third bullet point, you'll see some examples of equations and their solutions. In the examples, t is an independent variable, and x is the dependent variable. Thus, x is the name of the unknown function of the independent variable t. In these three examples, the letter c denotes an arbitrary constant. The fact that such constants appear as solutions is an indication that a differential equation does not, in general, determine a unique solution function. When occurring in a scientific problem, a differential equation is usually accompanied by auxiliary conditions that, together with the differential equation, specify the unknown function precisely. In this section, we're going to concentrate on one type of differential equation and one type of auxiliary condition. And the focus is going to be on initial value problems for a first-order differential equation. So the standard form here is x prime is equal to a function f of t and x, and x of a is given. That's some initial condition. X is a function of t, so when written in more detail, we have dx of t dt is equal to f of t comma x of t. The standard form is termed an initial value problem because t can be interpreted as time, and t equals a can be thought of as the initial instant of time. I want to be able to determine the value of x at any time t before or after a. So let's take a look at some more initial value problems. Here's some examples. The first one, you can see x prime is equal to x plus 1, x0 is equal to 0, and the solution we can see is x is equal to e to the t minus 1. A lot of different methods exist for obtaining these analytical solutions, but they're generally limited to special differential equations. When applicable, they'll produce a solution in the form of a formula, such as the ones in these three examples. Frequently, however, in practical problems, a differential equation is not amenable to solution by special methods, and we need to find a numerical solution. Even when a formal solution can be obtained, a numerical solution may be preferable, especially if the formal solution is very complicated or intensive to actually compute. A numerical solution of a differential equation is usually obtained in the form of a table. The functional form of the solution remains unknown insofar as the specific formula is concerned. In the examples, the form of the differential equation permits the function f to depend on t and x. Now, if f does not involve x, for example, if x prime is equal to 6t minus 1 and x1 is equal to 6, the differential equation can be solved by a direct process of indefinite integration. So consider x prime is equal to 3t squared minus 4t to the minus 1 plus 1 plus t squared to the minus 1 with x5 is equal to 17. Well, that's fairly easy to integrate. We can see that that's t cubed minus 4 natural log of t plus arctangent of t plus some constant c. We choose c so that x5 is equal to 17, and basically we find c is equal to 4 times natural log of 5 minus arctangent of 5 minus 108, which I'm certain is a fairly interesting value for c, but that gives us a precise solution to that differential equation. So why would we want numerical versus analytical solutions? Well, two reasons. One, the closed form solution may be very complicated, may be difficult to evaluate. And two, there may not be another choice. That is, there's no closed form solution that can be found. So consider the following differential equation. X prime is equal to e raised to the minus square root of t squared minus sine of t plus natural log of the absolute value of sine of t plus the hyperbolic tangent of t cubed. Now, you may be able to find a closed form solution to that with Wolfram. It may be computationally expensive, but basically, if we were to try to do this by hand, taking the integral and our antiderivative of the right-hand side, we could do it in principle, but perhaps not in practice, or it may not be easy. In other words, function x exists for which dx is equal to dt is the right-hand side member of the equation, but it may not be possible to write in terms of familiar functions. Solving ordinary differential equations on a computer may require a large number of steps with a small step size, so a significant amount of round-off error can accumulate. Consequently, multi-precision computations may be necessary on small word-length computers. Now let's take a look at an example of a practical problem. Don't worry, it's not rocket science. Oh wait, it is. Sorry about that. So, Newton's second law of motion states that F is equal to ma, where F is the force acting on a body mass, and a is the resulting acceleration of the body. Now, this law is actually a differential equation in disguise, because a, the acceleration, is the derivative of velocity, and velocity is in turn the derivative of the position. We'll illustrate with a simplified model of a rocket being fired at time t equals 0. Now, the motion is vertically upwards, as rockets tend to do. The height is measured using a variable x, and velocity is measured with v. Propulsive force is constant, 5370. Negative force due to air resistance is v to the 3/2 divided by the natural log of 2 plus v, and the mass is decreasing at a steady rate, and it's 321 minus 24 times t. That's because of the fuel burning off, and the fuel is completely consumed by time t equals 10. The downward force of gravity is 981, and when we combine them all together in terms of F equals ma, we get a nice differential equation with a set of initial values v equals 0 at t equals 0. We're going to develop methods to solve these types of equations in the succeeding sections. Moreover, we can also use mathematical software systems to solve this type problem. A computer program for solving ordinary differential equations produces a table of discrete values, while the mathematical solution, the analytic one, is a continuous function. We may need additional values within an interval for various purposes, such as plotting and interpolation. Interpolation procedures can be used to obtain all values of the approximate numerical solution within the given interval. For example, a piecewise polynomial interpolation scheme may yield a numerical solution that is continuous and has continuous first derivative matching the derivative of the solution. In using any ODE solver, approximation of x prime of t is available from the fact that x prime of t is equal to f of t and x. Mathematical packages for solving ODEs may include automatic plotting capabilities, because the best way to make sense out of a large amount of data that may be returned as the solution is to display the solution curves on a graphical monitor or to plot them on paper. As you may have guessed, there is a close connection between solving differential equations and integration. Consider the differential equation dx dr is equal to f of r and x, with x of a is equal to s as the initial condition. Integrating from t to t plus h, we can basically obtain x of t plus h is x of t plus the integral of t to t plus h of f of r xr dr. Replacing the integral with one of the integration rules from Chapter 5, we can obtain the formula for solving differential equations. For example, the trapezoid rule will give us one formula, and in that one, since x of t plus h appears on both sides, this is actually an implicit formula. Euler's method can be obtained by the left rectangular approximation. Integral from t to t plus h f r xr dr is equal to h times f of t x of t. In Euler's method, xt plus h is equal to xt plus h times f based on t and xt is used for xt plus h on the right-hand side. Then we obtain the Runge-Kutta or formula of order 2. We're going to see more about the Runge-Kutta methods in Chapter 7.2. Now, using the fundamental theorem of calculus, we can easily show that an approximate numerical solution for the value, or we can easily show an approximate numerical value for the integral from a to b of f of r xr dr. It can be computed by solving the following initial value problem for xb. Now let's take a look at the intuitive meaning of these equations. We can do that in terms of vector fields. Consider a generic first-order differential equation with the prescribed initial condition. So we have x prime of t is equal to some function f that depends on t and x of t. And the initial condition x evaluated at a is equal to b. Before addressing the question of solving such an initial value problem numerically, it's helpful to think about the intuitive meaning of the equation. The function f provides the slope of the solution function in the tx plane. At every point where f of tx is defined, we can imagine a short line segment being drawn through the point and having the prescribed slope. We can't graph all of these short segments, but we can draw as many as we wish in the hopes of understanding how the solution function xt traces its way through this forest of line segments while keeping the slope at every point equal to the slope of the line segment drawn at that point. So the diagrams of these line segments illustrate discretely the so-called vector field of the differential equation. Consider the differential equation x prime is equal to sine of x plus t squared with initial value x0 is equal to 0. Now, in the rectangle described by the inequalities, x runs between minus 4 and 4 and t runs between minus 4 and 4, we can create a picture of the vector field. So, mathematical software such as MATLAB can help show vector fields. Behind the scenes, this mathematical software carries out immense calculations to provide the vector field for this differential equation, and displays it correctly labeled. To see a solution going through any point in the diagram, it is necessary only to use the mouse to position the pointer on such a point. By clicking the left mouse button, the software displays the solution sought. By use of such a software tool, we can immediately see the effect of changing initial conditions. For the problem under consideration, several solution curves corresponding to different values are shown. And you can see that in this figure here. Depending on the initial value, you can get several different types of solutions. Here's another example of a vector field for the equation x prime is equal to x squared minus t. Notice the phenomenon of many quite different curves, all seeming to arise from the same initial condition of minus at t is equal to minus 2. This is an example of a differential equation whose solutions are exceedingly sensitive to the initial condition. You can expect to run into trouble trying to solve this differential equation with an initial value prescribed at t is equal to minus 2. So when you see t is equal to minus 2 here, you can see this branches off into a large number of possible solutions to that differential equation. So how do we know that the differential equation x prime is equal to x squared minus t, together with the initial value xt0 is equal to x0, has a unique solution? Well, there are a lot of theorems on the subject of differential equations that concern the existence and uniqueness questions, but one of the easiest to use is given here as Theorem 1. And from this theorem, we can conclude that the solution in question is defined for t minus t0 is less than some value beta. However, the value of epsilon in the theorem is at least beta divided by m, where m is an upper bound for f of tx in the original rectangle. Now, as promised, let's take a look at some Taylor series methods. The numerical method described in this section does not have the utmost generality, but it's natural and capable of high precision. In principle, we can represent the solution of a differential equation locally by a few terms of its Taylor series. Assume that our solution function x is represented by its Taylor series. So x of t plus h can be given by the Taylor series that you see on the slide. Remember that some functions, such as e raised to the minus x squared, are smooth, but they're not necessarily represented by a Taylor series at 0. So, for numerical purposes, Taylor series truncated after m plus 1 terms enables us to compute x of t plus h rather accurately if h is small and if x of t, x prime of t, x double prime of t, all the way to x nth derivative of x at t are known. When only the terms through h to the nth derivative of x t divided by m factorial are included, the method is called the Taylor series method of order m. Taylor series method of order 1 is known as Euler's method. Let's look at some pseudocode for accomplishing Euler's method. We can begin with the case where m is equal to 1. Again, this is Euler's method. And to find approximate values of the solution to the initial value problem, we use the first two terms of the Taylor series. So x of t plus h is approximately x of t plus h times x prime of t. Hence the formula x of t plus h is equal to x of t plus h f t x comma t can be used to step from t equals a to t equals b within step sizes of h equals b minus a divided by n. And on this slide we see the result of this. We see the pseudocode for Euler's method. Now, in this implementation we prescribe values for n, a, b, and x sub a. Of course, these can be modified to suit different problems. To use this program, we obviously need to implement a function for f of tx. In fact, let's look at an example where we do precisely that. So, here we use Euler's method to compute an approximate value for x of 2 for the differential equation x prime is equal to 1 plus x squared plus t cubed with initial value x1 is equal to minus 4 using 100 steps. We use the pseudocode from the previous slide and implement the function f of tx, as you can see over on the right. Now, the program yields x2 is equal to 4.23585. We can also execute Euler's method on this simple problem. X prime of t is equal to x, and x0 is equal to 1. Well, the analytical solution to that is pretty easy. X of t is equal to e of t because when you differentiate e of t, you get e of t back. So x prime is equal to x. We obtain x of 2 is equal to 7.3891. Now, the plot produced by this curve is shown in the figure. The solution x of t is equal to e of t is the solid curve, and the points produced by Euler's method are shown by the dots. Before accepting these results and continuing, we should ask some questions. How accurate are these answers? Are higher order Taylor series ever needed? Unfortunately, the answer to the second question is Euler's method is not very accurate because only 2 terms in the Taylor series are used, therefore truncation error is O of h squared. Okay, this example can be used to explain Taylor series methods of higher order. Consider again the initial value problem. X prime is equal to 1 plus x squared plus t cubed, x1 is equal to minus 4. Now, if the functions in the differential equation are differentiated several times with respect to t, then we get the results x prime is equal to 1 plus x squared plus t cubed, x double prime is 2x, x prime plus 3t squared, x triple prime is 2x, x double prime plus 2x, x prime plus 6t, and x to the fourth is 2x, x triple prime plus 6x prime, x double prime plus 6. Remember that the function of f has to function of x must be differentiated with respect to t by using the chain rule. If the numerical values t and x of t are known, these four formulas applied in order yield the first through fourth derivative. Thus, it's possible to work from this work to use the first five terms in the Taylor series. Since x1 is equal to minus 4, we have a suitable starting point. We select n equals 100, which determines our h, and then we can compute an approximation of x of a plus h, and the same process can be repeated for x of a plus 2h, x of a plus h, x prime of a plus h, all the way to x to the fourth a plus h. Finally, we can formalize these ideas into pseudocode on the next slide. And here's program Taylor to do precisely that. Now, basically, before writing pseudocode for a function like this, we need to determine the interval in which we want to compute the solution for the differential equations. In this example, the interval is chosen as a equals 1 to 2, which is equal to b, and we use 100 steps. In each step, the current value of t is an integer multiple of the step size h. The assignment statements that define x, x prime, x triple prime, and the fourth derivative of x are simply carrying out calculations of the derivative according to the calculations from the previous slides. Final calculation carries out the evaluation of the Taylor series using 5 terms. Since this equation is polynomial in h, it is evaluated most efficiently by using nested multiplication, which explains the formula for x in the pseudocode. This line here, you can see the nested multiplications. The computation t is equal to t plus h may cause a small amount of round-off error to accumulate in the value of t. This is avoided by using t is equal to a plus k times h. As you might expect, the results of using only 2 terms in Taylor series are not as accurate as when you use 5 terms. With 2 terms, we get 4.2358541, and with 4 terms, we get 4.3712096. The correct value to more significant figures is 4.36122, so closer to with 5 terms. So when we have the pseudocode described on the previous slide, we program and run on a computer, we may want to ask some questions about errors and accuracy. Particularly, what sort of accuracy can we expect? Are all the digits printed by the machine for the variable x accurate? Well, since we used the terms up to the fourth derivative, included, and the first term not included is the term with the fifth derivative, 1 over 120 h to the fifth derivative of x of t, we can work with h5 as approximately equal to 10 to the minus 2 raised to the fifth, or 10 to the minus 10th, affecting only the 10th decimal point. So our printed solution is probably accurate to 8 decimal places. Bridges or airplanes probably shouldn't be built this way, but for now this is going to be good enough. So, types of errors to consider: truncation errors, and these are due to using only the first few terms of the Taylor series. In the last example, the truncation error was 1 over 120 h to the fifth derivative of x at some xi, or order h to the fifth. We can also have accumulated effects of errors due to the accumulated effects of all local truncation errors and round-off errors. And although the round-off error is not serious in any one step of the solution, after hundreds or thousands of steps, it can accumulate and contaminate the calculated solution quite a bit. Remember that an error is made at a certain step, it gets carried forward into all succeeding steps. Depending on the differential equation, the method that is used to solve it, such errors may be magnified by succeeding steps. Various routine mathematical calculations of both the non-numerical and numerical type, including differentiation and integration of even rather complicated expressions, can now be turned over to computers. Of course, this applies only to a restricted class of functions, but this class is broad enough to include all the functions that you encounter in your typical calc book. With the use of programs for symbolic computations, Taylor series method of high order can be carried out without very much difficulty. If we look at the previously considered example we looked at in this section, the one with t cubed, x is equal to 1 plus x squared plus t cubed, we get a result of 4.37121105224969227234569569, which is pretty darn accurate. Next time we'll take a look at how we can avoid some of the analytical calculations and use methods called Runge-Kutta methods.